So section 11.2, some more fun with probability. And let's start with this hypothetical situation. In the future, this couple plans to have 3 kids. Then, what are the gender possibilities? Question. So, I actually did this in the last section, although it was with coins. And then it was heads, tails, heads, tails, tails, tails. There was all of those possibilities. So with the genders, let's say that it's boy and girl. So there's 2 possibilities here for the first child, and 2 possibilities for the second child, and 2 possibilities for the third child. So there's 8 possible. And for the total number or total possibilities or total outcomes or the sample space, I could write it like I did last time. It would be girl, 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 boy, etc. But there's another way to do that, and that's called a tree diagram. Like the branches of a tree. So this would be the starting point, and you could either label it that or just put a dot or something like that. And then they're going to have 2 kids. So one, it's possibly a girl, it's possibly a boy. So this row right here stands for their first child. Now when they go to have their second child, so suppose they already have this girl, they're going to have a second child, and there's 2 possibilities. It could be a girl or it could be a boy. Now another family or another hypothetical family had a boy first, and when they go to have their second, there could be a girl or there could be a boy. Notice also that I'm keeping them in order. So girl, boy, girl, boy, girl, boy. That way later on, if you need to count them and they're looking for something specific, it's a little more ordered. Anyway, so this is for the second child. And then from this hypothetical child, afterwards they could have either a brother or a sister, so it could be a girl or a boy. This one could have either a sister or a brother. This one could have either a sister or a brother. Either a sister or a brother. And then this is by the time they get to the third child. And that is what's known as a tree diagram. So, like when I wrote out tails, 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 heads, tails, tails in the previous section, well, that's right here. So this would be girl, girl, girl. So that's the first child's a girl, the second child's a girl, the third child's a girl. So could write it this sample space like this, or it goes girl, boy, girl. So girl, boy, girl. And we don't have to do all of these because the point of this one was the tree diagram, but you see what I mean. Then girl, boy, boy is another possibility. And when I follow all of those branches down, eventually I'd get to this one, to number 2, number 3, number 4, number 5, number 6, number 7, number 8. There's 8 total. So you can use this as a quick way to find out how many things you're supposed to have by the time you get down to the very end. Or you could just make it yourself, and then at the end you'll see there's 8 here at the end. So that the sample size is 8. So if I would have continued this, I would have gotten 8 when I followed the branches down. But like I said, we don't really have to do that part. Now, what if it was a slightly different situation? So for example number 2, now the situation is roll a die. Yes, I got a 5. And flip a coin. Heads. So I got 5 and then heads. Well, what are all of the possibilities? So 2 in heads, 4 in tails, a 1 and heads, etc. So use a tree diagram to create the sample space. So roll a die. Well, with a die, there's 6 possibilities. 1, 2, 3, 4, 5, 6. So you could get any one of those numbers. Now that's the first thing. So that's the starting point. And then after you roll a 1, then with the coin, it could either be heads or tails. So from this, it could be heads or tails. And from this, it could be heads or tails, etc. So before I count them to find out how many there are total, for rolling a die, there's 6 possibilities. And then flipping a coin, there's 2 possibilities. So that means that I should have 12 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good job, math. Then, using this tree diagram, find the probability that you roll an even number and get a T. So I already know that there's 12 total, so I can put that part, 12 total. And then how many have an even number and then a T? So an even number and then a T, that's 1. An even number and then a T, that's 2. An even number and then a T, that's 3. So there's 3 out of the 12. And if you reduce this fraction, that would be 1/4 or 25% of the possibilities. Now let's look at it a slightly different way. Just like this is a sort of a shortcut for all of this, perhaps we could even do this one as a shortcut. So what's the probability that it's an even and then we get a T? Well, how many of the numbers are even? So that's 3 out of 6. The word and turns to multiplication. And then on a coin, how many tails are there? There's 1 out of 2. And then 3 over 6, that reduces to be 1/2. And 1/2 times 1/2, you multiply on the top, that's 1. You multiply on the bottom, that's 4. So there's a second way to get the same answer. For example, number 3. Suppose at the ATM or when you log into some website, they are so secure that they require a 5-digit random PIN, personal identification number. How many such pins are there? So we could do it the long way, I mean the fun way, or we could do it the shorter way. Let's do it the shorter way. So first of all, with a personal identification number. So you go to your phone, maybe it wants you to type in a code, and you decide your code is 99999. It's not very secure, but I guess it's better than nothing. So my point is, somebody, for their PIN, they could just use all 9s. they could use the same number. So repeats are allowed. So when I do the 1, 2, 3, 4, 5 numbers, or 5 digits for the pin, then for this first one, there are 10 possibilities. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possibilities. And for the second one, there's 10 possibilities. And for the third one, there's 10, and 10, and 10. And all of those ands mean multiply. So let's see, this would be a 1 with 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. 100,000 possibilities. There's no way I'm doing a tree diagram for that. 100,000. So that means that if somebody found your ATM card and they tried to use it and they tried to guess your 5-digit PIN, the chances of them guessing it the first time, 1 in 100,000. They might try it again, which means they have 2 tries out of 100,000. They might try it again, 3 tries out of 100,000. At which point, the ATM should lock them out. So that was actually my question. I didn't write it down. Find the probability a person guesses your PIN within 3 tries. So the total number of pins is 100,000. And then they are going to try 3 different things. So they might try 88888. Oh no, that wasn't what? 777777. Nope, that wasn't it. 111111. Nope, they're locked out. So they get 3 different tries. So they get 3 out of 100,000. 3 out of 1, and then 1, 2, 3, 4, 5 zeros. So that's scientific notation saying move the decimal to the left by 5. So it's going to have 1, 2, 3, 4 zeros, and then the 3. So a very small chance that they're going to guess that PIN number. On to a similar but slightly different problem. Example number 4. How many phone numbers, phone hashtags, how many phone numbers start with the 831 area code? So with a phone number, it would be like 831 dash, and then there's 3 numbers dash, and then there's 4 numbers. I'm sure there's some good reason for that, but I don't know it. And then I guess it would be possible to have a phone number where it's 1111111, because like taxi companies and stuff, they'll do that. They'll have this like 7777, something that people could remember. So since all the numbers could be the same, that means that there's 10 possibilities here, and 10 here, and 10 here, and 10, and 10, and 10, and 10. These are already decided, so I don't need to use those. So then this would be 1, 2, 3, 4, 5, 6, 7. So that would be 10 times 10 times 10 times 10, 10. How many do I have? 1, 2, 3, 4, 5, 6. One more. Or in other words, a 1 with 1, 2, 3, 4, 5, 6, 7. That's 10 million phone numbers that are in the 831 area code. 10 million. That should be enough. Then, what's the probability of having this phone number? 831 dash whatever dash 1, 2, 3, 4. So what's the probability that that's somebody's phone number? So with this one, I only have these as choices. So that would be 10 times 10 times 10. So that is, the faster way to write it is 10 to the third. Now that's how many there are that would end 1, 2, 3, 4. How many are possible that end 1, 2, 3, 4. And the total is this. So the answer to the question is, the probability of having that is going to be, we got 10 to the 3 that are like that, and then this was 10 to the 7. And then you could reduce that by saying 3 of these are going to cancel 3 of these, which would leave 4. So that would be 1 over 10 to the 4th, which also means 1 over 1, 2, 3, 4, 1 over 10,000. Or in other words, let's see, this would be the tenths, hundreds, thousands, 10,000ths. So there would be a very small chance that somebody has an 831 area code and it ends with 1, 2, 3, 4. There is a chance, but it's a very small chance. And then one more example. Suppose that you randomly arrange the letters D, I, S, disc. So randomly arrange those letters. And then find the probability that it spells kids. Kids are cute. So, first of all, how many are possible? Now this is just a slightly bit different than the last one, because I've got 1, 2, 3, 4 letters. And I get to randomly pick from here. So I randomly pick and I got closest to the K. That was my randomly pick right there. So it got closest to the K. So it could be that a K goes first. But there's really 4 letters that I could choose from. So this is 4. Now once I take that letter out and I put it over here, then, don't diss me now, there's still 3 letters left. So that means that this is going to be a 3. And then once those are taken out, what I'd like to do is pick another one. There's 2 left. And then by the time I've taken 1, 2, 3 letters out, there's only 1 possibility left. And then multiply those. So this would be 12 times 2 is 24. So this is the total. And then in order for it to spell the word kids, it has to go in this order. K first, I second, D, and then S. So there's only one way to spell kids using those 4 letters out of 24 total. And then that one is already reduced, so you could just leave it like that. And that's the end of this section of probability.